gone fully virtual. So we've been hosting all of our events on Zoom and Hopin. And this has been an interesting experience for the organization as a whole, because especially for us with the London team, because up until now, our community was basically confined to London, but now we're seeing people from all over the globe joining our events, which is really exciting. And so for this event, we had the opportunity to partner with a lot of universities and offer tickets to students. And it was interesting to see from how many universities we have people attending. So we have University of Tehran, Azad, Kerman, Oxford University, Imperial College London, University of Vienna, Queen Mary University in London. And thank you to all the students who were excited about this session and who have joined us. A few other updates about women in general. We have a networking event coming up with all of the cities around the world on the 5th of March to celebrate International Women's Day and the Women History Month. And this is going to be a networking event with a number of tech companies who have sponsored us and who are joining us to offer help with recruitment, to talk about the culture of working in tech, what are some of the processes, etc. So if you are interested, this is being organized by Women Global, and it's going to be on March 5th. And the timing is such that it's in the morning Pacific time, so it's going to be like evening for Europe and Iran time zones. And with that, and if anyone doesn't know me, my name is Mahtab. I've been part of the London team since 2017. I really miss seeing all of you in person, but glad we still get to do these events. And I'd like to introduce Ida, who is the other team member on our team.
Hi, everyone. Sorry, I had a bit of a technical difficulty at the beginning. I'm Ida. I am also been volunteering with Women in Tech with this amazing team in London since last year. Welcome. I'm really excited for today's workshop event. Background-wise, I am a data scientist working in tourism industry in Expedia, and I'll hand it over to Gelare.
Thank you, Ida Jan. Hi, everyone, and welcome to our event. I hope you all are doing great and keeping safe in this crazy time. And this is Gelare, and I've been part of London team since late 2019, when we had just one physical event at Facebook, and then all went into virtual mode. I'm a data scientist. My background is in computer science, AI, and machine learning. I moved to London in 2015, and that was around the time that I get to know Mahtab as one of my best friends in London. And then I get to know Women of MENA in Technology, back then called Persian Women in Tech. I find myself attending to the webinars, to the events, sorry, not webinars, to the events every month. And thanks to the community, the amazing community, I get to know so many people who are, most of them are close friends of mine these days. I'm so happy to have you today, and I pass it over to our great Arife.
Great. Thank you, Gelare Jun. Hi, everyone. My name is Arife. So I've been volunteering with Women of MENA, previously known as Persian Women in Tech, since the very beginning when they launched a London chapter. But officially as the team member, I think I joined just less than 2 years ago. It's been an amazing journey for me. I've got to know many interesting people. My amazing friends are here. So I'm very glad. I'm just going to go through a few housekeeping rules for the event, and then I pass it to our amazing speaker of the day. So please please send your questions on the stage chat box. If they are related to the environment, to the platform that we're using, technical issues you have, me and the team try to answer to your questions and help you with the technical issues. By the way, Hopin best works on Google Chrome browser. So please use Google Chrome browser if you would like to join us later on in the sessions and you want to join and talk to us. It works better with Chrome browser. So any technical issue we will try to answer. Your questions about the webinar, please also send them on the chat box. At the very end of the session, we have a half-an-hour Q&A session, and we will try to go through all the questions that you've put there for our amazing speaker. Then we have the networking session. It's around 1:20 I reckon that we will move to the networking sessions. And we have 2 rooms for networking. One of them is for Women of MENA and our organization, the background, what we're doing, what are our goals, and you can join us and introduce yourselves and talk to us. There is another room that our speaker will be there to answer to your questions verbally and talk to you if you would like to. So that is an amazing opportunity as well. We will have a 10-minute break in middle of the workshop just to make sure you have enough rest between the sessions and it's not just too much for you. It's 10 minutes. Don't leave the stage. Just go for a walk around the house, get a cup of tea or a cup of coffee, and come back to stage. Within 10 minutes, we will start the meeting. That's all I have. So I'm gonna pass the stage to Saeid, our amazing speaker for today. And we are here to answer your questions, but we're gonna shut the cameras off so you only see our speaker and his material. Hi everyone again. Very sorry for the little glitch. I think we resolved the problem. I pass to Saeid, our amazing speaker, and we will start. Sorry about the delay again.
Hello, everybody. I'm Seyed Masoumzadeh, Senior Data Scientist at Lyst. And I'm really pleased to be invited to have a talk today. So we will have 2 45-minute sessions, and I will try to cover some cool stuff about neural networks and deep learning. This presentation was designed for the people have basic to intermediate knowledge in machine learning and computer science and also mathematics. So first, I would like actually to just let you know what is the outline of the presentation. I'm going to explain what is deep learning. Then we will find out what are intuitive problems. In third section, I will compare deep learning with traditional machine learning models. Then we will see where does deep learning stand in AI context. In the 5th section, we will see the historical trends in deep learning. And in the next section of that, we will find out how artificial neural network work, which needs some basic mathematical and information theory background. Then we will discuss about cost functions and optimization approaches in neural networks. After that, we will find out how neural networks deal with nonlinearity in the problems. And the last but not least, I will discuss about some deep learning architectures and their applications. At the end of this presentation, we will have a Q&A as well. So what is deep learning? This is a really big question, and I will try actually in the next couple of slides to explain that. In the early stage, in the early days of artificial intelligence, the problem was solved by artificial intelligence was difficult for human, but relatively easy for computers. That type of problems could be described by a list of formal rules or mathematical rules. But the true challenge actually was solving problems are easy for human, but hard for machine. This type of problems was the problems that human actually cannot describe them formally, such as recognizing spoken words or faces in images. And we call actually this type of problems intuitive problems. If I want actually to give an example to you about intuitive problems, for example, all the mothers know that when their child actually say lie, but if you ask them that how did you recognize that it was a lie or true, they cannot explain that. I mean, they could actually just recognize, but there is no explanation in terms of the rules for the mothers. So this type of problems actually is can be categorized actually in intuitive problems. The solution actually for this type of problem is deep learning, which allows computers to learn from experience and understand the world in terms of a hierarchy of concept, in which each concept defined in terms of its relation to simpler concepts. The hierarchy of concepts allows the computer to learn complicated concepts by building them out of simpler ones. If we draw actually a graph showing how these concepts are built on top of each other, the graph actually would be deep with many layers. So for this reason, we call this approach to AI deep learning. The right picture that you can see in the screen shows how deep learning learns through a hierarchy of concepts. So this is a network. It's like a graph, and we call it actually deep learning. And you can see in the bottom a layer that we call it actually a visible layer, which we feed the data to our model. And we can see actually in the next layer that we call it hidden layer, the algorithm could learn edges from the pictures. And in the second layer, the algorithm actually could learn corners and contours. And in the next one, it could learn actually the part of the objects. And then by having actually these concepts in a hierarchy way, the model actually can recognize that this picture is car or a person or an animal. When we talk about machine learning, we are referring to traditional machine learning algorithms because deep learning is a subdivision of machine learning, but is categorized as a modern type of machine learning algorithm. In the next slides, I will try to explain that what is the difference between deep learning and traditional machine learning algorithms. Imagine a simple machine learning algorithm which has been designed to predict the risk of cesarean delivery for pregnant ladies. Now imagine you have the information of 100,000 of patients. For example, a combination of surveys and ultrasound scan from uterine or womb. So for training your algorithm, you need to represent the information that you have from patients in the form of features. I'm emphasizing on the word feature, which is really important terminology in machine learning literature. Some example of features that we need to extract from the information, for example, could be the presence or absence of a uterine scar, or the, for example, the amount of amniotic fluid which around the baby. So the machine learning algorithm learns how each of these features of the patient correlates with various outcomes, which is the risk of cesarean in our case. The feature extraction, to be honest, is really hard because you don't know what type of features do you need to train your algorithm. But in deep learning, the feature extraction is a part of the algorithm. It's not something separate, which require human effort to identify that. This is the power of deep learning. This is why that we can give an ultrasound scan to deep learning and train it to learn the risk of cesarean without any human intervention. So the picture that you can see in the right-hand side of this screen shows this difference. So in machine learning, in traditional machine learning algorithm, we need actually to have a feature extraction part, which is sometimes actually a task that human needs to do that manually. But in deep learning, as you can see, the feature extraction is a part of the algorithm, and we don't need actually to have any human intervention. So now I want to explain that where does deep learning stand in AI? So as I mentioned, machine learning is a subdivision of AI, and neural networks is a subdivision of machine learning and deep learning. Machine learning actually is a subdivision of AI, and neural network is a subdivision of machine learning. And deep learning actually is a subdivision of neural networks. So please note, not any AI algorithm is machine learning. Not any machine learning algorithm is neural networks, and not any neural networks is deep learning. So I tried actually to give examples of algorithms that are exclusively belong to each part. For example, in the AI domain, we can actually mention rule-based systems. The rule-based systems are belong to the AI domain, but they are not actually belong to machine learning domain or artificial neural networks domain or deep learning. In machine learning, for example, we have regression algorithms or decision tree algorithms that are belonged exactly to this domain and not related actually to, for example, artificial neural networks. In artificial neural networks, we have shallow multi-layered perceptrons, which is actually related to exactly artificial neural networks domain. And in deep learning domain, we have convolutional neural networks, which is exclusively actually belonged to this part. So in the next slides, I will try to talk about the historical trends in deep learning. Deep learning has had a long history, has gone by many names, which reflects different viewpoints of philosophy. But there were two most important reasons that made deep learning really useful. One was the amount of available training data, which has increased dramatically. And other one was a very huge improvement in computer infrastructure. For example, cloud computing is one of the technology that helps machine learning domains and deep learning domains to grow very fast. As you know, in cloud computing, you will have access to unlimited actually computing resources, as much as you want. So by having actually these resources, we could develop some neural networks which were really complex, for example, 10 years ago, 20 years ago. But now actually it's easy for us to work with this algorithm without any hassle. So the computer infrastructure improvement actually helps deep learning domain too much. And had actually a really big impact on making deep learning useful. Here in the right side, you can see a graph shows increasing in a data set sizes over time since early 90s until 2015. And I tried actually to just mention three of these data sets which are really popular in a machine learning domain. And I'm sure that if someone actually studied in this domain, in machine learning domain, or worked as a data scientist, at least worked with one of these data sets. The first one is iris flower data set. So as you can see, actually, it has been introduced in 1920, which we didn't have any deep learning algorithm or machine learning algorithm, but the statisticians needed actually to have some data sets to investigate actually some cause and effects. So iris flower data set is quantifies actually a morphological variation of iris flowers of three related species, and has been collected by biologists, and including around 150 samples. So you can see that 150 samples is really nothing. I want actually to show you that how the number of samples increased during time, and how we entered actually to the big data era after 2000 and 2005, 2010. So the number of samples in the data really grow really fast. So you can see, for example, MNIST data set in the graph, which is a data set of handwritten digits, including actually some images from handwritten digits, which is usually actually used for training a handwriting recognition system, which including 280,000 images. And the next one is ImageNet dataset, which is actually a dataset including 14 million images. Yes, 14 million images, which is used actually for object recognition and classifications nowadays. It's a really actually good data sets that is used in academia and industry to develop some deep learning algorithms for object recognition and image classifications problems. Another graph that we have here, you can see in the right hand side, it shows actually increase in the number of neurons that we have in neural network over time. Since late 1950 until 2015, you can see how actually the number of neurons increased in neural networks, artificial neural networks, and you can compare how close we are to human number of neurons. So as you can see, in human we have 10 power to 11, and now actually in 2015, although this graph actually is a bit old, but in 2015 we could actually reach some algorithms which has actually a number of neurons very close to, for example, the number of neurons in bee or frog. In this graph, each number actually referring to an algorithm proposed actually in a specific year. So, for example, a simple perceptron algorithm proposed in 1958 just had around 10 neurons, while the GoogleNet, which proposed by Google in 2014, has about 10 million neurons. So and you can see actually this trend is obvious actually in this graph, that how actually the number of neurons in our algorithm increase during time. Now I would like to explain that how does artificial neural networks work. Arfejan, it would be nice actually to just let me know how much I have time, because I just actually missed the time.
Right. I'll let you know when it's close to the time.
Right. Thank you. So yeah, in the next slides, I will try to explain how does artificial neural networks algorithm work. And ANN actually here stands for artificial neural network. If I just mention in my slide somewhere, ANN is just referring to artificial neural networks. Yes, the things actually is getting serious here. So artificial neural networks are engineered systems, have been inspired by the biological brain. It is a directed acyclic graph in which the nodes called neuron. So, for example, the red circle and blue circle here called neuron in our network. And the neurons actually with the same functionality are organized in the form of layer. So as you can see, we have a layer called input layer and another layer called output layer, which includes actually same neurons that have actually the same functionality as I mentioned. The simplest neural network has two layers. Input layer, which is responsible to bring the initial data into the network, and output layer, which I will explain about that more in the next slides. So in neural network, similar to any supervised machine learning algorithm, we have two phases. We need actually to first train our model and then use that model to do some prediction for us. In our case here that I tried actually to show you as a slide, and the training phase is the one in which we show some data samples to the network to learn the correlation between inputs and outputs. In our case, the input is the coordination of a point in two-dimensional space, and the label or the output actually is its color, which would be actually green or blue. So as I said, the input here, as you can see, x1, x2, is the coordination of each point that we have inside the two-dimensional space, and the output actually would be actually the color for that coordination, for that point. So in the training time, we'll try actually to just show the samples to our model. For example, when we are showing this point to the model, we will try to label it with its color. When we are showing actually this point to the model, we'll try actually to label it with its color again. But in prediction phase, we will try actually to use network to provide a prediction for us regarding the unseen data samples. For example, if you have a point here or here or here that model actually didn't see and didn't already see that, we expect that the model actually can predict its color for us. So I hope that you could understand these two phases, because they are really important, the training phase and prediction phase. And the people actually have a background in machine learning. They know that how this works, but I'm just emphasizing actually on that for the people that don't have any machine learning background, because it is actually the one of the fundamental concepts that we have in machine learning. But how a neuron works, want actually to just go to the previous slide. Is possible? Yes, it's possible. So as you saw in this slide, as I mentioned, we have neurons and layer, and we want actually to just try actually to zoom in on this neuron to understand how this neuron actually works in our network. So in the left hand side, you can see a representation of a single layer network with just one neuron. It has two inputs and one output. In general, the neuron includes three sections. The first section multiply each input to its corresponding parameter, and the second section apply a summation on the output of the first section, as you can see here. And also, this section adds a bias to that, which I will explain that what is bias soon. And in the third section, we have activation functions. Basically, an activation function decides whether the neuron should be activated or not in a binary way, 0 or 1. However, in our case, we are not using a binary activation function. Instead, we use an activation function called sigmoid, which squashes whatever number as input to a number in range of 0 and 1, which can be considered as probability. And then we have another function outside of neuron here called threshold function, which converts the probability generated by neuron to 0 if it is less than 0.5, and to 1 if it is equal or greater than 0.5. So the output of a threshold function represents our classes here. So our single actually layer network here is supposed to solve a classification problem. So any sample that we have here, similar to what explained in the previous slide, must be classified in two classes. The output of this neuron, as I mentioned, is 0 or 1, and 0 or 1 here actually represents for us the color. So let's say that green actually is 0, and blue actually is 1. So for this reason, if a neuron wants to separate actually this blue point from green points, it needs actually to estimate a plane that you can see in the right hand side. But how a neuron actually can estimate actually this plane to discriminate this green points from this blue points. So let's see what would be the output of the second section of our neuron. For example, if we have two inputs, x1 and x2, based on the equation that you can see here, as I mentioned earlier, because I mentioned that this section try actually to do a summation on any actually input coming from the previous section, and this section actually just multiply our parameters or weights to the inputs. So the equation actually for this section actually would be something like this. If we consider actually xi as a representation of any input and theta I as a representation of the parameters that needs actually to be multiplied to that input, and also theta 0 actually here representing the bias that you want to add to this equation. So so based on this equation, the output of this section by having actually just two input would be something like this: x1 theta 1 plus x2 theta 2 plus theta 0, and it is exactly the equation of a linear plane in three-dimensional space, where theta 1 and theta 2 contributes in the slope of the plane, and theta 0 or bias contributes in intercept of that plane. So to adjust this plane to separate blue points from green points, we need to know the value of thetas. In other hand, our network must learn how to adjust the thetas to classify the green and blue samples. So in the next slide, I might actually mention these thetas as parameters. Sometimes actually we call them parameters of the network. Sometimes we call it sometimes we call them weights of the network. But I wanted actually just to let you know in the next slides, I might actually use actually different terminology for these thetas.
Thank you very much, Saeed.
Yeah, you're welcome.
Before you move on, I thought it's a good place to pause for maybe 10 minutes. I'm sure you want to grab a glass of water maybe, or a cup of tea. And please stay on the stage. And but yeah, have a 10 minutes break. We will be back 12:15 GMT time. I'm not sure what time it is in your area, but it's 5 minutes past 12 in London. So we give it 10 minutes and we will be back to continue this amazing conversation. Thank you, Saeed. Thanks.
You're welcome.
Saeed, please, I leave this to you to continue.
Yeah, Arfajan, I think, yeah, it is fine. So I can start. Let me share my screen. Yeah, I hope you can see my screen. If Arfajan can confirm.
Yes, thank you very much.
You're welcome. Yeah, so so we explained that how a single neuron actually works inside a single layer neural networks to discriminate blue line from green line for classify them. So as I mentioned, actually, I want to actually just come back a bit actually to the equation that I explained, because I want to transit to the next slide. So as I said, yeah, this neuron actually will output something like this: x1 theta 1 plus x2 theta 2 plus theta 0. And as I said, theta 1, theta 2 contributes in the slope of the plane, and theta 0 will contribute in the intercept. So the job of this neuron actually is to adjust this theta 1 and theta 2 and theta 0, because if we actually come up with some random number with this theta 1, theta 2, theta 0, it will generate actually a random plane, which might not actually can be able to separate this green point from this blue point. So we need actually to have them correctly, or we need actually to have them actually with the right value to have a plane, something like this that I'm showing you here in this graph, to just separate the blue line from green line. So as I said, in the next slides, we might actually call this theta's parameters sometimes. We might actually just sometimes call them weights, but don't be confused. Weights and parameters just referring actually to the theta's anywhere that I mentioned them. Okay, so the problem here is that how do we want actually to adjust actually this theta 1, theta 2, theta 0 in this neuron to just separate actually the points. For this reason, this neural networks needs two things, and that two things are cost function and an optimization approach. So a neuron actually, not the neuron, the network actually needs to have a cost function and also an optimization approaches to just adjust this parameters, adjust actually these weights, adjust thetas. In general, neural network algorithms involve optimization of some sort. Optimization refers to the task of either minimizing or maximizing a function by altering its parameters. We usually phrase most optimization problems in terms of minimizing that function, and maximization accomplished via minimization of a negative form of that function. The function we want to minimize in neural network called cost function. Sometimes actually it calls loss function as well, and which we show actually that as j theta. This is the way that we show cost functions. So we have a different type of cost function, but one of them is really popular and usually actually used for binary classification problem, and it is called cross entropy or log loss, or sometimes actually the people call them logistic loss. As I mentioned in my previous slide, from the test section of neuron here, the activation function provides a probability. So by having this probability, we can penalize actually that in a logarithmic way. For example, for class 1, a probability actually is closer to 0, must be penalized more. So you can see actually here how we actually just penalize this probability. The probability as an output of this section goes actually to the x-axis, and you will have actually the cost for that. So if the probability get close to 1, the cost actually will decrease, and if it goes actually towards 0, the cost actually will be increased dramatically. So this is the cost for just a true label or label 1, or as we mentioned, the label green, and for label 0 we have exactly a reverse graph, something like this, but I didn't actually put that here because I didn't want actually to confuse you. But if we want actually to write actually this loss function mathematically, it would be actually something like this, and it is actually y actually is just referring to the label of the class, and p actually referring to the probability. And also the probability actually is the output of this sigmoid function as an activation function here, which actually try to squash the output of this section, which is actually the weighted sum of the inputs plus bias. So the probability actually is modeled actually something like this here, and then actually goes to this function to provide actually this type of loss function. So this is why that we call it J theta. If you cannot see actually any theta in this equation, it is because the theta actually has been hidden actually in this probability in this function. So so let me just see that what I have to explain here from my notes. So in optimization part, yeah, this is the cost function part that I explained to you, that what is cost function exactly for this single layer network with one neuron. But in the optimization part, we want actually to use something actually to adjust actually this theta. So we want actually to minimize this function because it's the cost of this network by just altering actually these parameters. So the way that we use for optimizing them in most of the neural network algorithm, it's an algorithm called gradient descent. So as our real cost function here, as you can see, is multi-dimensional, and it's hard to represent that in this slide. I tried actually, for the sake of simplicity, I tried actually instead showing you a convex two-dimensional loss here, because if I want actually to show you actually if I want to graph that this function for you, it would be more than three-dimensional, and it is not easy actually to show that in the slide. So I tried actually to simplify that in just 2 dimensions to show you that how gradient descent actually works. So imagine that this is the loss function. Sorry, this is the loss with respect actually to the theta. And the graph actually shows that how actually we use gradient descent to find actually the minimum of this function. Gradient descent actually works in this way. So it tries actually to get derivative from this function with respect to the theta in an iterative way. So as you can see, this green line representing actually the derivative of the function with respect actually to theta, and this black point actually representing actually the theta. And then, so as you can see, whenever actually we can actually just find out that whenever we could find the minimum of this function, so the slope of actually this the slope of this line just shows actually the derivative of the function. When it is actually positive, it means actually that we are in the wrong direction, because when this line actually, the slope of this line actually is positive, it means that we are getting far away from the minimum. And when actually this slope actually is negative, it means that we are getting close to the minimum of the curve. So the derivative actually tries actually to show you the direction to us. And we have actually 2 different type of gradient descent. One actually is batch gradient descent. In the batch gradient descent, actually, we will have access to all data to minimize actually this function. But in neural network, actually, we have access to the data one by one, because we are actually showing actually to the model the samples, the points, as we had actually in the previous example, one by one. So we need actually to use another type of gradient descent called stochastic gradient descent, which actually try actually to take a derivative of the loss function with respect to the theta using actually just one sample that has been mentioned actually in this equation. For example, xi and yi representing the input and the labels for just one sample respectively. What's left actually for this slide? Yeah, let me check my notes. Yes, you might actually say that okay, I need actually just to mention that there are some other couple of issues in batch gradient descent, because actually we can actually just try actually to get the data and put them actually in a memory and then calculate that. you might be right, and you might actually say that why we are not using batch gradient descent. So putting actually the data into the memory actually would be sometimes expensive for us, because if we have actually lots of data, we will occupy lots of memory. So one of the reasons that we switch on stochastic gradient descent is that we might actually get less accuracy than batch gradient descent. But the thing is that we are not spending too much memory, and sometimes actually it is impossible to use batch gradient descent, to use all the data to optimize the function, because sometimes actually we have millions of samples, and each sample actually might have not millions, I mean hundreds of features. So if you want actually to put them in the memory, it could be really, really, really expensive. So I hope actually you understand the concept of loss function or cost function, and the way actually that I explained here, the cross entropy or log loss. And I wanted actually to show you that how actually the cost function is a function of theta. And then for simplifying that, I tried actually to show the function, actually cost function, in two-dimensional way. And I tried actually to explain that how gradient descent actually can work actually to find the minimum. It's a really easy concept. Just by taking derivative of the function with respect to the theta, you can find the minimum of any functions. And by just controlling actually, checking actually the slope of line generated by taking derivative. If it is negative or positive, it's just representing actually the slope of the line. And then actually, even when it is close to zero, you can actually find out that, yeah, you're close actually to the minimum of function, minimum of the function. You can stop optimization. So one of the stopping point of optimization would be having derivative equal to zero, which is not happening in all the functions, but you can actually have some criteria to define that. Okay, if for example if it is actually close to zero, stop actually optimization. One of the technique that you can stop training in your neural network. And I explained that what's the difference between batch gradient descent and stochastic gradient descent. In the batch gradient descent, as I said, you will try actually to update theta in an iterative way by taking derivative of the function with respect to the thetas using all the data, which is really expensive memory-wise. And a stochastic gradient descent, which usually used in neural network, just actually tries to update the theta by optimizing the loss function with respect to theta, and also each sample separately. Right. So this is the training process. You can see that how we used actually all the things that I tried to explain in the previous slides is just in just one slide. Feeding the data, which is x1 and x2, and its corresponding label to the model. In our case, as I said, our labels are 0 and 1, which represented green and blue color of the points, and then calculating loss and optimization, and then actually updating thetas or parameters, and we are doing that for any data samples. This process actually is we are doing actually this process for any data samples that we have. And the updating theta part actually called backpropagation. So we have feed forward, feeding data, calculating loss, optimization, and backpropagation to update actually thetas or parameters. So the next slide, I will try to explain that how neural network can deal with non-linearities, because the problem that I explained you in the previous slides just tried actually to solve a linear problem. The data points that we had in a two-dimensional space could actually be separated simply by a linear plane or linear line, but sometimes actually it is not possible to do that. For example, if you take a look at the graph B here, you will see that the blue point surrounded by green points, and you cannot use any linear line here to separate actually these points from each other. And as you can see, that the neural network needs to come up with a very more complex function to separate them. So one way to make neural network enable to solve non-linearities or solve the non-linear problems is to make neural network deeper by adding some intermediate layer, which we call them hidden layers. And this is the magic of neural networks. Deeper network has more ability to solve more complex problems. So as you can see, we tried actually to add some layers that we call them hidden layer to the model, to the network, to make it deeper. And we can actually do that more and more and more. So you can add more hidden layers to make your more neural networks deeper and deeper and deeper. And as I said, deeper networks has more ability to solve more complex problems. So welcome to the deep learning world. So as I mentioned, a simple neural network algorithm could convert it actually to a deep network by just adding actually some hidden layer. So from now on, I will try actually to focus on some deep learning architectures. The first architectures that I want to explain is convolutional neural network, or CNN, which is usually used for object recognition, image classification, and image segmentation. As an example, we want to have a network can recognize dresses, bags, and tops from each other. We have thousands of pictures as training data and a deep neural network, including multiple hidden layers to train. So in this case, for example, we have 3 hidden layers. The first step actually is to convert images to numerical values, because it might be a question for you that how we want actually to fit an image to a neural network, because neural network just can understand numbers. So you need actually to convert this number to some numbers, to some numerical values. It is not a really difficult task, as digital pictures contain a fixed number of rows and columns of fixed pixel, and each colorful pixel includes 3 numerical value known as RGB, which stands for red, green, blue. So if your picture, for example, this dress, as an example, for example, would be small or low resolution. So you can use a neural network, possibly deep, by having actually multiple hidden layer to predict the label for that. But if your picture are high resolution, including lots of details, you cannot use just a deep neural network. And you might ask why. Let's check an example. So yeah, these are two images. The first one here has a very low resolution, just 50 to 50 pixel. And because of RGB, it will generate 7,500 number of inputs. So, so if we assume that we have a hidden layer in our network, including 1,000 neurons, it generates 700,000 parameters. But in the second image, we have 1,000 to 1,000 pixels, multiple to 3 because of RGB, will provide 3 million inputs. And by having actually 1,000 neuron in a hidden layer, you will have 3 billion parameters. So the training would be really slow. We need a huge memory, and also there is no guarantee that the neural network learns properly. So, so we need actually to add something to our network, which called convolutional filters, which jointly trained along with the network as convolutional layers to extract important features from images. Also, we have another operation here, as you can see, called pooling, that we used actually a specific actually pooling method here called max pool. But this function is responsible actually for dimension reduction. So note that all this actually, all this network, including these convolutional layers that you can see here, which works as a filters to extract actually some important features from your image, will be trained end to end. So you don't need actually to do anything. So you need just to fit your model with a very high resolution picture, and then actually give the right label to that during training process. And all the parameters inside your deep neural network and also your convolutional kernels or filters will be trained together jointly. And then actually you will see actually a magic. After training, you will see that your network actually can recognize dresses from bag or top with a very, very, very high accuracy. So in this graph, you can see the history of convolutional neural networks and also their accuracy on ImageNet image database with 14 million images for the problem of image classification. The difference between architectures are in the number of convolution filters, the depth of the network, which actually resulted in different number of parameters in the network. So as I said, I want actually to just emphasize that these are some algorithm using actually convolutional network concept for the problem of object recognition and image classification And based on the number of filters that they are using, and also the depth of the network, how much actually they have hidden layer, for example, the number of their parameters changed. So the x-axis shows here the accuracy, sorry, the y-axis actually here showing the accuracy of the network, and the x-axis actually showing the year that this algorithm proposed by someone. And also the size of the circle refers to the number of parameters they have, and the colors shows to which family of algorithm they are belong to. Because, for example, Inception is a network that has been proposed by Google, and some other people actually tried to tweak this algorithm to make it better. So it resulted actually to another algorithm with a different name, but still actually they are belong to the same family. For example, Inception version 1, Inception version 3. They are two different algorithms, but they are belong to the same family. So I want actually just to leave you just 20 seconds, 30 seconds with this slide, because it has a lot of information, and I would like actually to let you be familiar with these names, because in deep learning world, machine learning engineers, data scientists usually use these names in a day-to-day life. So, and then it is good actually to be familiar with this name. So if someone actually say AlexNet or VGG or Inception, you will understand that to what algorithm actually they are referring to, and what are the characteristics of each algorithm exactly. So as I said, I will just leave you alone 20 seconds with these slides. Cool. So the next type of algorithm that I want actually to talk about that is autoencoders. In autoencoders, we have a network including two parts, encoder and decoder, and a hidden layer between these two parts. In this network, our output actually is the same as our input. So when we are showing actually a dress in the input, it will show exactly that dress in the output. So, and we'll repeat actually that for all our training data. After the model trained, we use actually that model in the prediction phase. And if we give that model an image, it will reconstruct that that image for us with some loss in the pixel. So as you can see, after training, if you show actually this dress, it will provide actually that dress with some low resolution, because it couldn't actually construct it very well. And you might actually say such a stupid network, because what it provides in the output is the same image, even with less quality. And you're right. The output is not useful in this network. However, we are not looking at the output. What we care about is the input for this layer for each trained image. And that input actually is the multiplication of the parameters learned before this layer and the output of the previous layer. So if we extract that as a vector for each image, we can actually transfer them into vector space and have a latent representation of the images. By having actually the latent representation of the images, we can do actually some magic. And you can see one of that magic in this slide. Yeah. So after actually representing them in a vector space, so you can actually see the similar clouds in terms of category, color, style, even material, that they are coming actually together. So by having the vectors into the vector space using a distance-based metrics such as cosine distance or Euclidean distance, you can simply develop a content-based recommender system. So if you, for example, choose a dress, I can provide you a similar dress in a fraction of time. Another extension of autoencoder is variational autoencoder, or VAE. In VAE, instead of learning a latent representation of images, the model actually instead will learn a latent distribution of the images by learning the mean and the variance of I'm trying actually to show you the distribution. Yeah, and instead actually of learning the latent representation of images, it tries actually to learn the latent distribution of that images by learning actually the mean and variance of that distribution. So one of the cool things that we can do in the prediction is just to sample data from learned distribution here and just pass it actually through the decoder part to get actually a new image. And then you can generate thousands of human faces that are not exist in the world. So none of them actually are exist in the world. We trained actually model with some real images. We tried actually to learn actually the distribution of the images in this layer by learning actually the mean and variance of that distribution. And then by having that distribution, you can actually sample some data and then pass it actually to the decoder, and it will generate actually another picture for you. But that picture is not belong to any human in the world. This is completely fake. We have many other deep learning architectures, such as recurrent neural networks, generative adversarial networks, graph neural networks, Siamese neural network, with thousands of applications in image processing, video processing, and natural language processing. Also in recommender system and ranking, they are actually really useful. In this presentation, I tried actually to give you some information about the basics of neural network and introduce you some popular deep learning architectures. Every day, a new approach in deep learning proposed by someone somewhere, and this field actually is expanding and expanding. Thank you, and I'm ready actually for any question that you have.
Thank you very much, Saeed John. I'm just gonna ask the London team to join the stage before we continue.